Hello students, and welcome to a tutorial on PyTorch. We will be using PyTorch, which is a library of Python to implement neural networks, and specifically would be implementing convolutional neural networks and doing some examples on them. So let's begin. Actually you can find help about and some tutorials about PyTorch using these links. PyTorch actually works like NumPy, but it has some advanced functions as well. And before using PyTorch, remember that you first have to install it. You can install it standalone. You can install it in your basic Python, or you can install it using Anaconda. So let's try these cells one by one. We first import the NumPy and PyTorch. You can see the version of the PyTorch that we have is 1.7.1. You can check whatever version you have. So PyTorch actually implements tensors, which are like NumPy arrays but with some advanced functions. But they also include almost all the functions that NumPy arrays have. So let's create a 5 by 3 tensor with random values, and remember that tensor is kind of an extension to vectors, but vectors are of limited dimensions while tensors have more dimensions. For example, you can define a cube-like tensor with 3 dimensions, or a tensor with 4 dimensions, and so on. So let's create a matrix-like tensor with the 2 dimensions, 5 rows and 3 columns, and let's print it. So we have a tensor here which is just like NumPy arrays, but here you see this word tensor, which differentiated from the NumPy array, and it has 5 rows and 3 columns with some random values. We can construct a matrix filled zeros, and we can also define data type of the values. For example, we can use long data types. So let's do that. Now we have created again a 5 by 3 tensor, but now all the values are 0 and the data type is long. We can also take a tensor from a list of values. For example, we can use this list with 3 values 1, 2, 3 and convert it into a tensor using the object-oriented dot operator of torch and tensor. So we have a list with 3 values, and it would convert it into a tensor. And you can see this is just a one-dimensional tensor with just 3 values, or just 1 row. We can also create a tensor based on another tensor, which means that if we have a tensor with a certain size and data type, we can create a new tensor which would get the values of the data type and the size of the tensor from the original tensor. So let's create a new tensor by invoking this method called new underscore ones with the dimensions 5 and 3, and let's print it. And then we create another tensor with some random values, but based on the shape and data type of x, or we can also change the data type or override the data type with the, let's say, float. So in the original tensor we have we had a 5 by 3 tensor which was or with all the values equal to 1, and then we created a new tensor where the values are some random values, some random float values. We can get the size object of a tensor by invoking dot size. So let's see that, and you can see the size of this tensor is 5 by 3. Operations on tensors are very similar in syntax to NumPy. For example, we can add 2 tensors with using plus operator, or using the dot add operator. In both cases the results would be the same. So as you can see, we already have had a tensor x, and we created a new tensor y, again with random values on both of the tensors of the same size, and then we add these tensors just like any normal matrix addition or array addition, and then using these two methods, the plus operator and the dot add operator, and both of these gives us the same results. PyTorch also supports in-place operations, and the method names end in underscore. So for example, we can use y.add_x, which would actually add tensor x to tensor y, and it would replace all the values in tensor y. So instead of creating a new tensor x plus y, we convert the tensor y to x plus y. So if we print it, you can see this is the same one as x plus y, or dot add x comma y. So here we are actually using the in-place operations of tensor. Indexing on tensors works just like NumPy arrays, as you would expect. You can index them by their dimensions separated by commas. For example, if we use this code, it would give us the first 4 rows and all columns. So as you can see, first 4 rows, sorry, not the first, and all 3 columns here. So actually 4 would not be included, so it would be row 1, row 2, starts from 1, 2 and 3. So we get 3 rows. Let's see some check the data types and casting of tensors. So for example, if we create a 3 by 3 tensor with ones and the data type is double, we can print it. Then we create a new tensor from the same tensor A, but now the data type is B long. So and then we can print, we can check this the data type of this. So the original tensor, we have all ones, the data type is float 64, which is double, and then we create a new tensor B, and which is where the data type is long, and new tensor C, where the data type is integer. All of these tensors have the same values but different data types. We can use tensors to do interdivisions, and it works just like Python and NumPy. For example, we can divide 3 by 2, we can divide a NumPy array of size 3 on another NumPy array of size 2, or we can divide a tensor of size 3 on value 3 and value 2, sorry, not size but values, and all of these would give us the same results, except that because the last one is a tensor, so it would be preceded by the word tensor here. You can find the documentations on various data types. PyTorch supports all the data types that Python does, and you can find all the documentation on this link. Let's see some more useful operations on tensors. We can use .view, which can be used to resize or reshape the tensors. So it's similar to the method .reshape of NumPy. So let's create a tensor with random values of size 4 by 4, and let's convert it to a size 16, which means just one row with 16 columns and so on, and then another one where the size is would be 2 by 8. So let's see these sizes. If the original one was 4 by 4, the same tensor would resize to 16 and then again resize to 2 by 8. This -1 actually infers that this dimension would be inferred from the other dimension. So since the other dimension is 8, so this would automatically become 2, because 16 by 8 is 2. If we have only one element in a tensor, we can find that element. We can directly print that element by using method.item. Let's see if we have, let's create a tensor x, which is x.sum, which means that we are using the tensor that we created before, which is of size 4 by 4, and x dot sum would add all the values of all elements and create one value. So x would still be a tensor, but the size would be 1, and we can print it, and we can print its value by x dot item. So the difference between these two outputs are the first one is preceded by the word tensor, the next one doesn't have the word tensor because it just gives the value. We can also convert between NumPy arrays and PyTorch tensors. So for example, if you have already have a NumPy array, and if you want to convert it to a tensor, we can do that, or vice versa by using .numpy. So let's create a tensor torch.ones 5 of size 5, then print it, and then we can create we can convert this to a NumPy array, but by using the method .numpy. We can also use add.add_1, which is a method in NumPy which would add the value 1 to each value of the original tensor. So let's see. Okay, here it's interesting to note that when we added 1 to the NumPy array, it is also added to the PyTorch array and to the torch to the tensor as well. Let's do the vice versa, where we actually convert NumPy array to a tensor by using .from_NumPy and do this addition of value 1 again. The difference between the two methods for NumPy and tensor is that for NumPy it's add_, but for torch, for the tensor it's add with parameters in parentheses. So let's print these two, and again when we apply this +1 on one array or on array, it is also automatically applied by the tensor as well, and vice versa. If we have GPU, we can use CUDA and we can use tensors there as well. So let's first see if you want to check whether you have CUDA on GPU, you can use this simple code that would check if there is CUDA. So since I am on a desktop with no GPU, so it says that I don't have a CUDA. So let's skip this part. Okay, and this is a very important, the next one is very important concept, which is called autograde, or which is, as the name suggests, used for automatic differentiation or gradient calculation. Since we would be using PyTorch for neural networks, and more specifically for deep learning or convolutional neural networks, where we have to calculate gradients for backward propagation, so we need this function autograde for that. You can go through these guidelines to understand how this automatic differentiation works. So let's try them. It's very easy. You just have to create a tensor, just a normal tensor, but we also use this flag requires _grade equal to true, which means that the gradients would be calculated and they would be tracked. So let's print this. So it's just like a normal tensor, but it also says that the gradient required is true. Now we can perform some tensor operation and see if we can calculate the gradients automatically. So let's use this tensor to create another tensor y, so which is just a function on x, y, a simple function x plus 2. So then we can later on differentiate this function y with respect to x. So let's print this. It's adding a backward derivative to our tensor. Okay, now let's print this grade functions, which is a add backward, which is an object, a function which calculates the local gradient. Let's do some more operations on the tensor y. So we can have series of computations in forward direction, and we can calculate all the gradients in the backward direction. So it's just like a computational graph that we studied before. So let's define another tensor z, which is 3y square, and another tensor out, which is z dot mean, which would give us a scalar value, a single value tensor with the mean of all the values in z, and let's print it. So the first one gives us 27, 27, 27, which is from here, like 1 plus 2, 3, and 3y square is 27. And the next one gives us 27, which is the mean of this tensor. And each one is accompanied with the corresponding tensor. For example, the gradient, the corresponding gradient function. For example, it's multiplication backwards, and here it's mean backward. So the actual function that is applied on the tensor is tracked. It's stored in history, so that in the backward direction its gradient is calculated. Okay, we have a method that is dot requires underscore grad, which changes an existing tensor's requires underscore grad flag in place. So if we invoke this method, and if the requires underscore grad flag is true, it would be changed to false. If it's false, it would be changed to true, and so on. So let's do some examples. We create a tensor A of size 2 by 2 and random values. Then we create another tensor A, which is 3A divided by A minus 1, and we print A dot requires underscore grad, which would tell us the current status of the flag requires underscore grad, and then we can change it to true, print it again, and then create another tensor and print that tensor and the corresponding flag. So for the first one, the requires underscore grad flag was false because we didn't use it. For the next one, because we changed it to true, so it's true now. And for the tensor B, because we applied an operation which is a multiplication and a sum, so the final operation is, since it's a sum, so it would create a gradient function with sum. Okay, so let's back propagate now. We have used some functions on the original tensors to create an output. Now let's see if we can see the gradients calculated at each step of the backward propagation. So for this tensor out, which was let me see, okay, which is here, which just contains one value 27. So let's calculate this, and let's print the gradient. So the gradient is 4 by 4 tensor with values 4.5, 4.5, 4.5, and 4.5. How did we get this value 4.5? So we can see that the out is a mean of the input zi, 1 by 4 times sigma zi, and zi itself is equal to 3xi plus 2 square. And if we put xi equal to 1, zi is then 27, because the original tensor was all with values ones. Therefore, do divided by d partial o by partial xi is 3 by 2 times xi plus 2, the gradient that we can calculate by hand. And if you put the value xi equal to 1, it gives us 9 by 2, which is equal to 4.5. So we can actually do many crazy things with autograde. So let's try some. We have a tensor x with requires underscore grad equal to true, and size 3 with some random values. Let's apply some function y, which is 2x, and let's apply some operations on y by using this while loop. That is, since the norm of the y is less than 1000, you'd keep on doubling the y, and then once the norm reaches 1000, we can print this y. So let's see. So it's a tensor with 3 values, and the grade function is backward multiplication. Since at each step we are doing some multiplication, actually doubling the input, so the final operation is also a multiplication. Okay, let's see some more examples. Let's create the gradients of a tensor with three values, 0.1, 1 and 0.001. The data type is float. Invoke the backward operation, which would calculate gradient, and let's calculate this gradient, which gives us these three values. We can also stop autograde from tracking history on tensors with requires underscore grade equal to true by wrapping the code block in with torch.noGrade. So let's say if we print this, if we use x square dot requires underscore grade, and if we with torch dot no underscore grade, it would stop the tracking of the gradient calculation. So originally it was tracking the gradient calculation, and then when we use the method dot no underscore grade, it stopped tracking the gradient. Okay, now since we are now familiar with simple operations on tensor, so now we can use tensors to create some neural networks and perform different operations on them. PyTorch has this method called NN. It has a library which actually is used to create different types of neural networks. An NN module actually contains layers and a method forward with input and returns an output. So if we use a forward operation on the module, it takes the input and produce the output at the final stage of the neural network. And this module can contain many layers. These layers could be neural convolutional units, pooling units, linear units, and so on. So a typical training procedure for a neural network is as follows. We define a neural network that has some learnable parameters. The parameters are weights. We iterate it over a data set of inputs. We process the input through the network, compute the loss at the end of the network, which is by comparing our output to the correct output. Then we propagate gradients back into the network's parameter, and remember we can do that because we have the autograde facility, and update the weights of the network by using a simple update rule. For example, a weight minus learning rate times the gradient, which is just a normal stochastic gradient update method. So let's start with defining the network. Let's start with the simple neural network. So with the import torch, import.nn, and dot functional as f. Let's create an object, let's call it net, which would use the nn.module. Let's define the different layers of this network. Let's define first convolutional network, which is a 2D convolution. It takes one input and produces 6 outputs, and this convolutional network actually consists of 5 by 5 convolutions. So at a single time, the size of the window in this convolutional layer would be 5 by 5, which is k by k actually, if you remember from the lecture. Then let's create another convolutional layer with 6 inputs and 16 outputs, and again 5 by 5 convolutions. Here you can see, since in the last convolutional layer we have six outputs, so the next convolution layer expects 6 inputs because it would be the next layer after the first layer. Then let's also define some fully connected layers, FC1, FC2 and FC3, which are linear layers. The first layer takes an input 16 by 5 by 5, and this is because our output was 16. There was 16 outputs and each output was 5 by 5, and the output of this convolution, this fully connected layer would be of the size 120. The next one would take this output as the input and produce an output of size 84. The next one would take this as an input and produce an output of size 10. So if this is our, let's say this is our final layer, which that would mean that this neural network can be used as a classifier with 10 classes, because our final layer contains 10 outputs. Okay, let's define the forward operation on and some interburst operations on this neural network. We used max pooling, 2D max pooling twice, and inside before that max pooling we also use ReLU, which is rectified linear unit for activation. So that means that this first one would be applied after the first convolutional layer, and after the first convolution layer the output would be passed through a ReLU and then passed through a max pooling. Then the next one is used after the second convolutional layer, which means after calculating ReLU we would pass it through a max pooling. Then the next one is a flatten function, which would convert a tensor output, a multidimensional tensor output, to a vector output, so that it can be used for the fully connected layer. Then we can use ReLU on these fully connected outputs as well. And then finally we can return the final output. So let's save this as an object called net, and let's print this. So as you can see, the net is a neural network containing a convolutional layer, and then another convolutional layer, then 3 fully connected layers, and inside these fully connected layers we have these ReLU, flatten, and max pooling. Okay, so when we define a neural network in PyTorch, we just have to define the forward function, because the backward function, where gradients are computed, is automatically defined by using autograde. So we can use any of the tensor operations in the forward function, and then use the backward operations, and since the gradients are automatically calculated, so we do not need to further do anything about it. We can learn about the null neighbor parameters by using the net.parameters. So let's see. Okay, here you can see that we have 10 parameters. We have 10 null neighbor parameters because we have 10 layers. There are 2 convolutional layers, 3 fully connected layers, and each fully connected layers is accompanied with max pooling and ReLU. So overall we have a range of 10 different parameters that we need to learn or update. The size of this is 6 by 1 by 5 by 5. So let's continue. Let's try a random 32 by 32 input. So let's create an input which is a tensor, a random tensor of size 32 by 32, and produce the output by applying the neural network in the forward direction on this input. So this is our output, and as we can expect, the output is of size 10 because of the final layer contained 10 units, which was just normal perceptrons. Okay, this is very important. We need to zero the gradient buffers of all parameters and before we do any back propagation. And since when we would be training the neural networks, we would be calculating gradients at each iteration for each sample or mini batch. So, and once we do that and we move to the next sample, to the next iteration, the gradient that were calculated in the previous iterations still remains there in the gradient buffers. So we need to zero the gradients before each operation. So you can do that by .0_grade. So let's calculate out.backward, where the input was torch.rand and 1 to 10. The output. So for a random output, let's calculate these gradients. Okay. we can use the we can actually calculate the gradients. Okay, to calculate the gradients we also need a loss function. So our final function actually would not be the an activation function that calculates the class labels, but a function after that which would be calculating the loss function. So we already defined many different types of loss functions in the class. So let's, for a simple example, let's use the simple loss which is called MSE loss, or mean square error loss. That is the difference between the actual label and the actual output and our predicted output would be calculated and squared and then summed over the whole data set. So let's create the output with our input that we generated randomly. Let's also create a target output which is a random 10 dummy target, random 10 values. Let's also change its shape so that our predicted output is in the same shape as the target output, and then calculate the MSE loss. Let's call it using the criterion MSE loss. So the loss would be calculated by taking the inputs which are output and the target, and let's print it. So our loss here is 1.3763, and our since we already mentioned our final function was MSE loss backward, so the gradient function is calculated on MSE loss backward. If we follow the loss in the backward direction, we can actually see a computational graph that is going like this. We have input, then a convolutional layer, then ReLU, then max pooling, then convolution, then ReLU, then max pooling, then view, which would just change the shape, then a linear, then ReLU, then linear, then ReLU, then linear, and then MSE loss. And in the backward direction, a gradient is calculated at each step till we reach the till we get a gradient with respect to the input, with respect to the parameters of all the layers. So when we call the loss dot backward, the whole graph is differentiated with respect to the loss, and all the tensors in the graphs that have requires underscore grade true will have their dot grade tensor accumulated with the gradient. So let's, for illustration, let's follow a few steps backward. So let's calculate the final gradient, which is MSE loss, gradient on the MSE loss. Let's calculate gradient on the next function in the backward direction, which was a linear function, and we can also look at the gradient function on the next function, which is before the linear function or a ReLU function. So we get these three objects. Okay, so let's use these. Let's also calculate the gradients on different functions or layers of this neural network. So we can calculate the gradient, for example, on convolutional layers before the backward and after the backward, and calculate the loss. So before the backward propagation, since we zeroed all the gradients, so we have these values equal to 0 for all the gradients. And after the backward gradient calculation, now these values are changed to the actual gradient values that were calculated during the backward propagation. Okay, now using PyTorch, we learned how to create tensors, how to do different operations on tensors, and how to create a neural network, and how to calculate the gradients at each step of the neural network, and how to use them for back propagation. The only thing that we are left with now is to learn the parameters of the network through updates, or another means. Now we need to use the gradients that we calculated in the backward propagation to update the parameters of each layer. So updating the weights, they are very simple. You just have to subtract the learning rate times the gradient from the previous weights at each stage. It can be easily implemented using the simple code, or we can also use the different options that PyTorch gives us. So these options are in the optimizers, which is torch.optim, and we have different options for the optimizer. So let's use stochastic gradient descent update method, and on the all the parameters of the network, and let's define a learning rate of 0.01. So in our training loop, we would first need to zero all the gradients, then create the inputs in the forward direction, create the output in the forward direction for a given input, then calculate the loss given the input and the output and the target, then compute the gradients in the backward manner, and then use the optimizer to step update our previous weights with our new weights by using the gradients that we calculate in the backward propagation, and then you can finally calculate the loss after the update. So this would actually calculate a tensor which gives us a loss, and the gradient function is MSE loss backward. Okay, it's very important to note again that the gradient buffers creates the previous values. So before each update step, before calculating gradients, we have to zero all the gradients and all the values in the optimizer as well. Okay, so now let's train a classifier. Let's use some example data. Let's use CIFAR10, which is a data set of images, labeled images. Each image is 32 by 32, and there are 3 channels because there are colored images. So each image can be represented by a 3 by 32 by 32 tensor, where 32 by 32 is the dimensions of the image, and 3 is represents the channels, so for red, green, and blue. So we can load these images, we can use packages such as Pillow or OpenCV, or there are inherent packages within PyTorch that we can use for these images, which is called Torch Vision. So let's load and normalize the CIFAR10 dataset. First, let's import these libraries Torch Vision and their methods transforms. Okay, so this would download and verify the dataset CIFAR10 and also normalize it and convert it into a training set and a test set. So in these data sets, we have 2 kinds of data. One is the images, and the other one is their corresponding labels. And the classes there are 10 classes, which are the labels of these images: plane, car, bird, cat, deer, and so on. Since this data set was already downloaded on my computer, so it didn't take much time, but when you run it on your computer, it would take probably a few seconds or a minute to download the data set from the internet. So let's see some training images. Let's see how these images look like. So we define a function IMShow. First, get an image from the data set. First, unnormalize it, because the images in the data set that we have are normalized. Convert it into a NumPy array and use IMShow of the PyPlot to plot these images. So here you can see we have 4 images and their labels: truck, cat, truck, and plane. Okay, if we want to train our data or model on GPU, we can define the device as CUDA by using torch.device method, and if it's not available, it would automatically and by default be converted into CPU. And if you don't use this device conversion, it would still remain CPU. But if you have GPU and if you want to use GPU, then you have to use this line of code, otherwise it doesn't matter. Since we don't have a GPU here on my PC, so it won't change anything. Excuse me. Okay, so let's define a convolutional neural network as we learned before, but now as per our example inputs and outputs. So we have a convolutional layer. Look at this, note this 3, which is actually represents the 3 channels of the inputs, and each input is of size 1, and then it's then again of size 32 by 32. Then we have a pooling layer, a convolutional layer, followed by a convolutional layer, and followed by 3 fully connected layers, and so on. And then there is a flattening layer and ReLU layers, etc. And since we want to use this code for GPU as well, so we can export it to GPU by using two device that we already defined. And since we don't have GPU here, so this device is by default our CPU. Okay, after defining this neural network, we need to define a loss function in optimizer. So for loss function we use cross entropy loss, because the data that we have is images, and for optimizer or for the update method we use stochastic gradient, and with learning rate 0.001, and also using a momentum of 0.9. Let's train this network. Let's also track the time to see how much time this network takes. Okay, so for we loop over the data set for multiple epochs. So let's say we use 3 epochs with running loss 0 and start the counter. Then for each mini batch we get the inputs and their corresponding labels from the data. We export this input to device and the corresponding labels to the device, and remember that the device contains our neural network that we defined already. Use optimizer, zero all the parameter gradients. Then all that we have to do is apply forward operations, backward operation, and then optimize operation. So in the forward operation, all the layers of the neural networks or the functions are applied on the inputs to calculate a final output. In the backward operations, gradients are calculated for each step, and in the optimize operations the weights are updated at each step based on the gradient and the previous weights. So this is our forward operation, which is just applying the neural network on the inputs, then calculate the loss, and then the backward, and then the optimizer. Let's print some statistics by updating the running loss for every 2000 mini batches. And we defined mini batches as 4, so that means that each mini batch uses 4 images at a time. So when we that means in each iterations we use 4 images as input to calculate 4 outputs, and then calculate the loss. Based on the loss we update the parameters for those based on the results on those 4 images, and then use the new parameters, the new network, updated network, on the next 4 images, and so on. And then we print the loss for each 2000 mini batches. So here you can see for the first 2000 mini batches our loss is 2.252. The time it took was 6.85 seconds. Then in the second for the second 2000 batches the loss is 1.937, and then it keeps on decreasing, and for the last 2000 mini batches our loss is 1.297, and it almost in all these steps take almost the same time. Okay, so now we have a finished trained neural network which we can now use on test images and to see how they perform on the test data. We can also save this trend model to use it later. For example, we can copy it and take it somewhere else, try it on another device, and so on. So here we can save this using the save method of the PyTorch. Then we can also load it by using dot load. We don't need dot load right now because we already have the model in memory, but it's just to see how this works. Okay, now let's see this network on the test data. So let's first try it on a few samples of the test images, and then we can try it on all of the test images. So we get some images from the test images using test loader. These are images and their corresponding labels. Let's also print them. And remember, we have a mini batch of size 4, so it prints 4 images and their corresponding labels, which are ground truths. Now let's predict the labels of these images using our neural network. So as you can see here, the predicted are a little bit different than the original labels. It's almost very different. So for example, ship is predicted as car, plane is predicted as ship, and cat is predicted as frog. But let's try another one, probably for a different set of images. It could get us a better output. Let's try again. Okay, so let's move on for now. Okay, now let's see how our network performs on the whole data set. So let's start with tracking the number of correct predictions with correct and the total predictions with total, and started with 0. Let's start a counter with torch.no_grade. Then for data and test loader, this would actually load 4 images from the data set, and then we export it to the device, which in our case is CPU. Use the forward operations to calculate the outputs for each of these images, and their corresponding predicted labels, and then we can actually increment the correct if the label is correct. And let's calculate the accuracy. That would be the number of correct labels, correct predictions divided by the total predictions multiplied by 100. It's going to take some time because we are now using all the images. Okay, so the accuracy of the network on the 10,000 test images is 54%, which is better than chance, which is for our case. If our network was just performing on chance, the accuracy would be 10% because we have 10 classes, so 1 divided by 10 is 10%. Okay, let's see what are the classes which performed well and the classes which did not perform well. So although our overall accuracy is 54%, not very good, but still pretty good to go for our initial example network with not much training. But we can now check on which classes the network is performing well and on which classes the network is not performing so well. So let's run this code. So till the code runs, we can look at different how these different lines works. So we load the data, which would be at a time 1 mini batch, export it to the device, create their corresponding outputs, and then check whether the predicted output is equal to the actual label, and if they are equal, this class correct label would be incremented, and in any case this total would be incremented. So at the end you'd get so the class correct, which are uh, uh, list of 10 values for so which where each value corresponds to the correct prediction for each class. So these would be incremented to a final value which would be the number of correct classification, correct prediction for that particular class. So let's print these accuracies. So the accuracy of plane is 41%, the accuracy of car is 82%, and we have a very bad accuracy for dog. The best accuracy we get is for car, and the worst accuracy that we get is for dog, and so on. You can also look for different informations in these PyTorch tutorials for data loading and saving models. Okay, now since you learned how to implement a neural network, a deep learning neural network for different types of data and how to do training, backward propagation, and updating the network, and then testing on the test data. Here is a new concept which is called transfer learning. Transfer learning is basically when you train a model or somebody else trains a model on some data set, and then use that model on some new problem. So instead of creating a new neural network model from the scratch, we can use an off-the-shelf pre-trained model and just tweak it a little bit, modify it a little bit to our current problem. So that kind of learning is called transfer learning. So we can use this. For example, there are pre-trained model available within PyTorch. For example, ImageNet, which consists of 1.3 million training images, and then we can fine-tune it to our smaller data set to get better performance. So what you have to do is now is you copy the code that we just saw from steps 1 to 5 by creating the new by loading the CFR10 data set and doing everything. But now we have to replace the custom model, the neural network model that we created, with a pre-trained model from torchvision.models. We have to modify this pre-trained model to our CFR10 dataset. The CFR10 has 10 classes, but ImageNet has 1000 classes. So that means the final layer should be changed so that it has 10 units instead of 1000 of the pre-trained model. Similarly, the CFR10 images dimensions are 32 by 32 and on 3 channels, but the ImageNet dimensions are 224 by 224, which means we also need to change the input layer as well. So once we do these changes, then you can retrain this model, this pre-trained model on CFR10, and then test it on the test data set. So this would be your homework. I'd give you a week to do this homework, and once you are done with these exercises in this tutorial, it would be very easy to follow. The homework would be much easier than this exercise. So then you can use this Python notebook to do all your work and then submit your results as a homework. Thank you very much. If you have any questions, please use my email, or you can use the chat option in the MS Teams, and I'll try to answer them as much as possible. Thank you very much and good luck.